Hello. Hi, everyone. And thank you so much for choosing my talk this morning. My name is Anton Bjöörn, and I am a software engineer at Swedish Space Corporation, which is a bit of a mouthful. Swedish people usually know it as Rymdbolaget. We're a space corporation owned by the Swedish government, but we're not a government agency, so kind of like Systembolaget. Yeah. My talk today will be about space safety, about the situation in orbit and how SSC has committed to projects to mitigate the situation and try to find solutions, especially ones who are using very sophisticated software solutions to be able to solve and tackle this problem. So just briefly, I started my engineering career at the Royal Institute of Technology in Stockholm. I studied engineering physics, but I always had a huge passion for computer science, so I picked a computer science master, did machine learning for my master's program, and then worked as a full stack developer. And then I ended up at SSC, working with hardware, so that's me. I guess you can tell which year this picture was taken. Since then, I've had the pleasure of working very close to hardware. We have built a fully autonomous telescope called the Øredev station down in at our site in Western Australia. Once again, there I am. And I'm going to start out by just trying to explain why we built this station. Why do we need this sort of equipment that looks at stuff in orbit around us? And why do we need great software to be able to do this? So we have a huge problem right now in orbit. We're launching more stuff than ever. There's been a total of about 23,000 launches since 1957, when we started launching stuff. There's about almost 60% of it is still up there. So we're not very good at removing stuff once we launch it. About 45% of those are still working, which is actually pretty good news, but that's because most of what we launch, or most of what we use up there, up in orbit, was actually launched quite recently. So a lot of the old stuff is just dead satellites floating around. There have been about 6,700 launch attempts. You can tell we're launching more satellites, of course, than we're launching rockets. And now we're seeing, so in total, there have been about 100 launches per year on average since 1957. But nowadays, we're launching more than 200. 2023 was the record-breaking year with 223 launches. So this still doesn't sound that crazy, right? Like 100 on average, and then 200 now. But we'll get to that because we're tracking about 45,000 objects regularly in orbit around Earth, which you can tell there's a bit of a difference between that and the amount of satellites we have up there. And around half of all the satellites that we see in orbit now are made by one company, SpaceX. They're launching an insane amount of satellites. They're aiming towards 12,000. They already have 6,500 up there. And possibly they're going to expand it up towards more than 30,000. So, as I mentioned, the amount of launches has gone up. But even looking at a graph like this, you don't really get a sense of the issue. It kind of looks a bit uniform, almost like we were launching more in the 80s than we have been recently. But when you look at the actual amount of tonnage or the number of payloads that we're sending up, you get a very different picture. Because we're not just launching more rockets, but we're also launching way larger rockets, which can move so much more stuff. And we're also tending to send up a super large amount of small satellites rather than big ones these days. This creates problems. So the 45,000 objects that I mentioned that we track regularly as humanity, as a collaboration, a lot of those are debris. We have millions of objects when you include debris and not only satellites. So as you can see, it's more than 34,000 that are larger than a decimeter. Of course, if you get hit by one of those in orbit, it's bye-bye. But even smaller objects, such as all the millions of millimeter-sized objects, can do a lot of damage if you're in different orbital regimes. This is an example from the cupola on the ISS, which was hit by, what is believed to be a fleck of paint. But because it was traveling in a different orbit, that's what it does. It can shatter glass. So yeah, not good. Most of these debris objects, they come from anti-satellite tests. Some of them, every launch results in debris. You have rocket stages that end up in orbit and they stay there. But a lot of countries, including the US and Russia and such, they like to test out their weapons. So they use their anti-satellite weapons and they shoot a satellite to show that they can do it. And that results in an insane amount of debris. It creates a debris cloud that spreads out over orbital regimes, and it creates, well, objects of all different sizes. So the problem you end up with in orbit is that you have to avoid hitting all of this debris and other satellites. Now, if you're in an airplane, you just do this, right? It's like, what's the issue? You see it coming, you turn the other way. So why can't we just do that in space? Well, when you launch a satellite and you notice that we are on a collision course with something, you have to predict it way ahead of time, which is difficult to do. Then we have to fire our thrusters on our payload or our satellite. And we have to do that way ahead of time. The later you do it, the more it costs. So we do that. Then we fly around. So now you can see the orbit has changed. We have we have raised our apogee on the other side of the planet. That's the highest point of your orbit. And then when we come around to the point where we did the maneuver, we have to undo the maneuver. And all of this costs a lot of money. I mean, you're paying an insane amount just to send a satellite up there, and then you're wasting your fuel just dodging debris. Right? So in general, satellite operators don't want to do this. Another problem we have is that the position of a satellite is not very well known. It's not like a GPS system where you know roughly where your car is, right? Or you can know to like a meter position where you are. In space, that doesn't really turn out as well. Usually, you know the position of your satellite to like at best tens of meters. It's rare to have very, very good precision. And this uncertainty of where your satellite is, it grows over time. So even after just 2 or 3 days, the information about your orbit is deemed useless. You have to constantly reobserve or re-ascertain your position. This is, of course, greatly exaggerated. You don't just drift that much. But over time, you can get the extreme differences, such as like, we don't know if the satellite is going to re-enter the atmosphere or if it's going to stay up. And one way to solve this is to do what we did. We built a telescope. So you can take pictures of your satellite to determine where it is. And if you do that, you might not even have to maneuver, because like in this case, you notice that, oh, actually, I reobserved my satellite, and we're not on a collision course, so all is good. We don't have to do anything. And of course, you can predict further and further ahead in time as you reobserve where your satellite's going to be. Now, when you're driving a car, and you meet another car, you know which way to turn, because there are rules governing who should turn, who should give way, right? There's no such thing in space. Here's an example from 2019, where the ESA satellite Aeolus was on a collision path with the Starlink 44. ESA calculated that it was a 1 in 1,000 chance of collision, which is 10 times higher than their threshold for when they have to do something. And Starlink or SpaceX said it's fine. They weren't worried. So what ended up happening? Well, ESA had to move their satellite. And that cost them a lot of money, of course, because as I just showed, maneuvers are expensive. So this is a problem. So why should ESA have to move their satellite? Like, who has the initiative? Who should be paying for this risk mitigation? And how big a risk are we willing to accept? It's hard because nobody owns space, right? And what if it wasn't another satellite? What if it was just a piece of debris that was floating around up there? Who is responsible then? Are you responsible for the debris that you left up there? Do you have to now pay the ESA to maneuver their satellite because you left a piece of garbage in space? And that's not the worst part. The worst part is that, yes, we are tracking about 45,000 objects, but the worst part is all the stuff that we don't see. Because there's a lot of objects, as I showed, there's millions of objects, that we don't even know that they're there. So this is an issue. And what can happen is that if you have a collision, that collision, of course, results in more debris. And then that debris can collide with other satellites or other pieces of debris. And anyone who has studied nuclear fission kind of recognizes this image. This is sort of the same thing as what happens in a nuclear reactor. Because if one atom splitting results in more fission, then if that coefficient is just slightly larger than 1, you get a catastrophic event, which is like the reactor going critical. Or in this case, our entire near orbit environment going critical, which is called the Kessler syndrome, which means you can end up with something like this, where you envelop Earth in a shredding cloud of debris, which would quite fast wipe out all satellites, which brings a lot of issues, because we rely on satellites for a lot of things these days. For example, monitoring extreme weather events, which are becoming more and more common, for getting our weather updates, for communication, for GPS, of course, which everyone might think of. But what you might not think of is that the global shipping lanes, all the cargo ships across the world, they rely on GPS. They don't know how to navigate without GPS. So if the GPS systems get knocked out, global shipping and trade just stops, like overnight, which would be a catastrophe. And of course, bank payments also stop, because a lot of bank payments also rely on timestamps sent by the GPS system. Another problem with not knowing where stuff is in space is that we can't hold anyone accountable for what they're doing. If you can't show what someone is doing, you can't enforce law. So, for example, Russia has been doing a lot of things recently, such as their Luch satellites, which have been sneaking close to other satellites. And we don't know why, but maybe they're eavesdropping on communication or trying to do some interference. And when the Russians also like to, when they launch a satellite, they launch one, and then that payload splits off a secondary payload, which we don't know what it is, and then they split off a new one. So they might have officially stated that we're launching Cosmos 2570, but then they end up launching more stuff that was not publicly announced. And they're not the only ones to do this, of course. Another interesting thing is that we don't actually have a good picture of what the status of our satellites are. This is an interesting example with Intelsat. In 2019, they reported a fuel leak on their satellite. So the company ExoAnalytic, they took their telescope and started looking at it to see what's actually going on. And let's see if this video wants to play. Nope, of course. But I'm prepared for this. What you see in this video, you can look it up yourself, is that satellites in orbit look like dots because they're so far away. And you can see clearly in the video how there's a catastrophic event. Like there's some sort of cloud, then everything goes calm again. And then you get this. This is not a fuel leak. This is much, much worse. It's possibly a catastrophic fuel leak. And then it keeps just like shredding this cloud of possibly fuel, but I mean, it's very evident when you see this that this satellite has been lost. Eventually, they admitted that yes, they had lost communication with the satellite. But this just shows that, like, I'm not saying that Intelsat were lying. It's just that we don't know what's going on. It's not like the stuff is so far away that it's really hard to know what's happening. All right. So what do we need to solve these problems? Well, we need really precise tracking, so really high quality measurements of satellites so we know exactly where they are. We need lots of data, lots of sensors that can collect this data, so both quality and quantity. We need diverse sensors, so both telescopes and radar stations, because they complement each other. We need data sharing, which is really not the case today. Like, you can get public data, but a lot of different data collectors, they're not sharing their data with anyone. So there's a problem with transparency there. And we need transparency. We need both the sharing and the transparency. So what I mean by transparency is that we don't just need to know what you observed, where you observed the satellite. We need to know how you observed it. What are your error bars? Like, what was the methodology or method behind it? Because otherwise, if somebody tells me it was there at that time, I can't use the information because I need to know what are the uncertainties, because I know for sure it's not precise, a precise measurement. And then we need fast observations because things can happen quickly. If, for example, with the fuel leak that we saw, you need to be able to react quickly to something happening. If there's a collision coming up or an event like that, you need to be able to observe it as soon as possible so that you can act as soon as possible. So what I'm trying to say with all of this is that there's a huge need for good software. Because if you have really great software and really great architectures for these systems, all of this becomes possible. So at SSE, we decided to take a step into this field with the AWARE station, the Automated Western Australia Reconnaissance Telescope. No, it's not a perfect acronym. So we built this. We started this project in 2021 when I joined SSE, and then it was completed in September of 2022, and I guess fully operational in 2023. We had to do some hardware upgrades. The design requirements for this was that it, of course, needs to be extremely reliable because we're placing it super far away, down in Australia. We can't. It's not only far away from us; it's also far away from the nearest city. So you need to put telescopes in remote locations to get the dark night sky. We need it to be adaptable because we want to create a network of these stations. So if we're building one, it's a one-off. But if we want to build 20, we might have slightly different hardware configurations in different places. And so we don't want to have to rewrite all of our software just because we changed the camera on the telescope. We need it to be extremely responsive. As I said, we need it to be quickly schedulable and it needs to be able to react quickly and start observing. We need it to be completely automated because, as I told you, there's already 45,000 objects tracked, but if you want to track potentially hundreds of thousands of objects, you can't do that by hand, so everything has to be automated. And we needed to leverage academic expertise, which is a bit of a weird one, but I'll explain more why, because the field of tracking space debris is really a topic for research still. Like it's not something that we know exactly how to do. So this is what the data that we collect looks like. If you speed it up, these photos are taken over several minutes. You can tell it can be quite noisy data. We're probably passing close to the moon there or a cloud, so we're getting way overexposed. It's a highly cross-disciplinary field. One person alone cannot write like the software suite or all the tools that you will need to solve the problem. So, for example, you need to do image analysis. We use machine learning for this. You need to do astroreferentiation because we actually use the stars that are streaking past in the background to position the satellite. You need to know orbital dynamics because you need to be able to associate your observation with a known object to know if it's a new object or if we're actually reobserving something that we're already tracking. And if you're going to have a dozen or 20 sensors across the world, you also need really good schedule optimization to be able to distribute these observations to the different stations. So, some of the design choices we did to be able to fulfill these requirements. We use mostly Python. Mainly because we want to include students and PhD students and researchers into the project. And we want them to be able to work as closely as possible with our code as possible. So if we ask them, they would say, use MATLAB, which is not an option. So the second best thing is that a lot of people, when they study nowadays, they are taught Python, which is good. We containerized our software as much as possible into different modules, so that, for example, we have one container talking to the cameras. And like I mentioned earlier, if we have to switch out the camera, we just make a new module. We don't have to redesign the whole system. We have a lot of hardware, but we try to connect it all to one server in the station, which runs Linux, which we try to do for stability reasons. And we put a powerful GPU into the station so that it can run all of the processing actually in the station, which I will talk about more later. And lots and lots of storage. These images that we take, I think they are about 500 to 300 megabytes each, and we can take 100 frames a second. which we usually don't do because there's no point in taking images that quickly, but we usually take images at a rate of 1 per second at most, so 1 hertz, which is, I mean, you realize it's an insane amount of data. So how do we deal with this remoteness of the station? Well, we knew from the beginning that the hardware was going to bug out and glitch and break, and we were going to have issues. So the main way that you deal with this problem is pretty obvious. You have a crew on site for maintenance and emergencies. No matter how badly you want to have a completely automated system out there, it's impossible. You need a crew. But you don't want to bother them too much. They have better things to do, and you don't want to call them for an emergency when they're at home. So this is the most common solution to all of our problems. Have you tried turning it off and on again? Which is why the most important thing is to have remote power cycling of all hardware. It's sort of obvious, but we actually specifically ordered remotely power cyclable power distribution unit, PDUs, and we got ones that weren't. So for the first year of operating the station, we didn't have that, even though we wanted it. So it was definitely the most important thing to have. You need remote access control for the servers, so that even if you lose contact or it crashes or you're having issues, for example, Dell's iDRAC is very good, so that you can completely remotely manage your server. And you need your server to be fully functioning when you reboot it. Now, of course, everyone has had the experience where they have a production server, which nobody has rebooted in like a year, and then you reboot it, and then it doesn't work. So this is something that we focus a lot on. And when you're working with hardware, especially with a lot of USB devices, one way to ensure that this works is that we set up Øredev rules. So I'm going to try to take a little bit of a technical deep dive into that now. So Øredev is the user space devices on a Linux system. So you can get a lot of information about your devices that you have connected by running a command like this. Then you want to locate some attributes for that USB device that are unique either to the physical port or to the USB device. Some devices have a serial that you can use, which is great. But if you don't have that, which for several of the devices that we plugged in, they didn't have that, then you can actually take the physical port on the computer and you can create a rule for that physical port. So as long as the crew on site doesn't like move the USB to a different port, you're good. You're going to be able to reconnect to the device when you reboot. And then you add these rules, which can look like this, for example, where you say that if a device on the subsystem USB matches this serial number, we're going to add a tag to it. And if it also uses this kernel and has that tag, we're going to create this simulated link, or symbolic link called my device. Then you reload the rules. You re-trigger the mapping of your devices. And then you check that you have this in your /dev directory, the my device link that points to that USB device. And then, in your Docker Compose file, instead of mapping that actual name, tty_usb0, you map the actual symlink. Because the symbolic link will always be the same when the computer reboots. So therefore, this container here, this device interface container, will always get a connection to that device, which is good. So, more about dealing with remoteness. You need surveillance cameras. The amount of times that we have been able to tell on this that something is wrong is a lot. It can be as simple as we were looking at our images and we don't understand why they're so overexposed. And then when we look at the security camera, it turns out that somebody left the lights on in the dome. So, yeah. And all your critical devices need to be accessed directly. So what I mean by that is that you don't want to access your PDUs, your power distribution units, or your surveillance cameras via another server. You want them to be accessible in parallel. So, because if your server or some computer dies, which they tend to do, you can no longer reach those devices. So it's that simple. So, of course, it's the network switch can fail as well, but that's way less likely to happen. So, and some things that were important to us. We sometimes lose connection to the site because it's far away. And the connection is not very good. That's why we need a lot of disk on site. so we can process the data locally. And we need virtual screens, because when you buy, a lot of the hardware that we bought for this station was bought commercial, just off the shelf, that when we put it together. And a lot of those pieces of hardware, that you get really good software. You get some good control software, and you want to use that. But the software has a GUI. And if there's no screen connected, the software crashes. So we found a good way to always have a virtual screen up, which is that we used containerized virtual screens that we share between the containers. So it can look something like this. You have your virtual screen container in your Docker Compose file. It uses this image in our case. It's a web top image. You give it a user ID, which should be the same as the container where you're running your software that needs access to the screen. And then you share the /temp folder, the TMP folder, with you bind it to a volume in your Docker setup. Because in the temp folder, of course, you have the .x11 folder where the screen socket goes. So you're sharing that between containers. So here's what the application would look like. So both of them are getting this virtual screen mount into the temp folder. And then they have the same user ID, and they connect to the same display. And then, like magic, your application will always show up on that screen. And you can also do RDP, or you can remote into it by just going to that port number in your web browser, which is nice if you want to, do manual control, which we don't want to do. But so this is what the server looks like. You can tell we have a lot of USB ports, a lot of different PCI cards in it. We chose to have only one server and connect everything to that server because there's no way you're going to avoid having a single point of failure. You're always going to have a single point of failure. So we decided that it's better to have one big computer which controls all the devices instead of having like 10 small Arduinos on like a network and then having some central computer somewhere else coordinating them. And this has turned out to be great because we have we've of course had a lot of issues, but we've actually never had the server crash, knock on wood. So because it's unavoidable to have single points of failure, you want fewer points and you want stronger points. That's my biggest suggestion, because that will make your system more reliable. If you truly want redundancy, you're going to have to build 2 telescopes. Like, there is no way around it, because the telescope can break or the camera can break. So that's my advice. And to strengthen this main point of failure, then we, like I mentioned, we containerized all of our software into modules. So each device talks to one container, and we try to isolate it as much as possible so that we don't get interference between them. Testing, of course, and using a stable Linux OS. And the way we handle crashing is that we want to be able to crash as fast as possible and then reboot as fast as possible. So if we have an issue, which happens, all of our containers are designed so that they crash fast and they can get back to the state they were in as quickly as possible. Because sometimes the hardware will throw errors that they're out of your control, essentially. So we try to keep our software as stateless as possible when it is possible, so that whenever you reboot it, it will go back straight into the same state that it was in. Now, the biggest challenge that I faced in this project was that I was assigned to writing the monitoring control software for a bunch of hardware that I didn't have when I started, which was kind of scary. It's like, in about a year, we're going to go down to Munich, we're going to do the factory acceptance test, and we're going to plug everything in and see if it works. So I started writing simulators. I tried to simulate all of the devices as thoroughly as possible, and I contacted the suppliers to get the documentation, of course, but in the best case scenario, I actually got into contact with developers at the suppliers, which you'd be surprised how often you can get that connection, actually, if you pay enough for the hardware, I guess. It's very expensive stuff, usually. So that was great, because, of course, there's always a bunch of inconsistencies and vagueness in the documentation for the software. And you can get around all of that. And sometimes they even give you their own simulators, which is awesome, because then my job is done. But then you notice, of course, that the provided documentation simulators are always or usually wrong. So you need to adapt the simulators once you actually get the hardware to improve your development environment. So I'm going to deep dive a bit into how I set up simulated USB devices on a Linux system. So all of the device interface containers have a switch where you can set an environment variable to true to use them in simulation mode. So on container startup, I check if this is true, if we're running it in simulation mode. And if that is the case, we use the SOCAT tool on Linux to set up a simulated socket or device socket or link in the dev folder. So you can see here we're creating this dev/my device, and we are connecting it to this other device called my device server. And then when we start my device simulator, we connect it to the server part. So this means that the device simulator script will connect to that one, and whatever it sends in there can be read from the dev/my device. So the name implies that it goes to the server. So this is what a basic simulator script can look like. So we're using PySerial here to open up that serial device. We're reading code points. We're looking for a start of message byte, a SOM, so the start of the message. Then we read a certain number of bytes, and I believe I just made an example here that replies with the same message that you send. And then, yeah, that's the send function. So if you do this, you get an awesome feature, which is that your development environment is going to work like exactly the same as production. Because in your development environment, your script, your device server that talks to the device, it's going to talk to this dev/my device, which is linked to this other device, which is then on the other end, you have this simulator, which is pretending to be a USB device. So all that we do when we switch over to production is that we just replace that device with a real device and hope that they talk exactly the same, which is the idea of the simulator. And yeah, this allows you to do really, really good, thorough end-to-end testing. So for example, this is what our development environment ends up looking like. We have our front end, we have our back-end services running with the database and the scheduler, and then we have the monitor control software. We can simulate several stations. Each station is then connected to a bunch of simulated devices. So it's sort of like beyond full stack, right? We have the full stack, and then we have like hardware at the end as well. So what you can do is, you can request data in the front end. You can get the scheduler to book those observations on the stations. The station, they all pick up their own bookings and start to actually simulate a real observation of a satellite. We have simulators that fake images of the satellites. We actually had a PhD or a thesis student who wrote a simulator for us to simulate satellite imagery. So we get these simulated fake images from the observation, which we can then process as well, because they are actually simulated well enough that you can do data processing on them, which generates fake data, fake tracking data, which we move back to our backend services and then deliver to the customer. So if you have good enough simulators, you can essentially test everything in development as if you were connected to the real system, which is awesome. And on a more low level, you can actually test the observations. So as I mentioned, you start an observation, you can check if the mount that controls the telescope, is it moving? Is it pointing in the right direction? Is the mount tracking? You're checking your simulators to see if everything's working. Does it run without error? Did we get to exposures? Because if the configuration was wrong, maybe we didn't get any exposures. So simulators. And they allow us to run the same tests in development as when we connect our hardware. So one of the first things I did when I got access to the hardware for the first time was that I plugged in all the hardware, I switched all my containers, the use simulator, to off, to false, and then I ran the tests with the real hardware to see if it worked. And it didn't. But that's when you notice what is the difference between my simulator and the real hardware. And then you adapt your simulators, so that eventually you get to a state where your simulators and your hardware act the same. So you can truly test and develop for your hardware. So this is some more examples of what the images can look like. They can be quite varied. The previous one was a low orbit satellite, and this is more of a geostationary satellite. You can see actually multiple satellites in this image. So we do data processing in the station. And the first step to that is that we do astroreferenciation, which looks at the stars and informs the position. Then we do image calibration, which is applying biases of the camera, essentially, to the image to improve the signal-to-noise ratio. Then we run object detection using a YOLO V8 model. And this runs in real time. So for every image that comes in, we do this. We process it, and we segment it to find the objects. We have a Tesla T4, NVIDIA Tesla T4 in the station, which is more than enough to do this. The YOLO V8 model was a thesis project that I supervised by Suryateya Darbamala. He is from the Blekinge Institute of Technology. We used a dataset of 300 images taken with the actual telescope. And we annotated it, or he annotated it, I should say. That was a lot of work, of course. And then we also trained it on various conditions. So we made sure to include, windy conditions, cloudy conditions, when this satellite overlaps with the star, so it's hard to detect. And did a lot of data augmentation as well to make sure that this model is not actually specific for a specific camera. It can work on any satellite image or image of a satellite. The way it's actually applied is that we split the image up into 320 by 320 pixel sub-images, because that's what the training set looked like. We apply the model to each sub-image. And then sometimes we end up with something like this. You can see that you might misinterpret that little dot there as a satellite, but it's actually a star that is poking into frame. So then we actually recenter around each detection to check, was it really a satellite, or is it just a star? So just like a confirmation step. Once we have the coordinates and the object detections, we have an analysis software by Lorenzo Mariani from the Sapienza University of Rome, which associates detections between images into cohesive tracks and correlates them to known objects. And then produces, this is what we want in the end, a TDM tracking data message with angles and times for the object. It also does photometric analysis and orbit determination, but that's beyond the scope. Log collection. I'm realizing I have to speed up a little bit here, but log collection for a complicated system like this, when you have many different containers, of course, very, very important so that you can monitor everything. And it's important to do this both in production and in development so that you can, the amount of times I've been able to solve a bug because I had my ELK stack, Elasticsearch log/Kibana, running locally, and I could see all the logs from the different containers side by side. Very, very important. And it allows us to create dashboards like this just to get an overview of what's happening in the station. So here we have actually all of these squares here. They show the status of a device interface talking to one of the devices. And a green 0 means it's all right. A yellow 1 is a warning. And if it's a red 2, then you can't observe. It also allows us to track the performance of the station over time. So are we seeing any biases? Are we seeing any loss of quality over time? We, as I mentioned, try to automate our operations as much as possible. So we use forecasted weather data. And we calculate the visibilities of satellites from the station. And then with those two, and also requests for data, so you can add like, okay, I want an update on this satellite. I want tracking data within the next 2 days. So if you know the forecasted weather, because we can't see the satellite if it's cloudy, and we check if there are visibilities, then we can use our automatic schedule optimizer, which was a thesis project by Erik Heneström at the Royal Institute of Technology, which creates this. As you can see, we have a very tightly spaced observation bars here showing when we're observing which satellite. And it's prioritizing them based on like the quality of the visibility and the length of the visibility. In order to be able to have a completely automated operations, no matter what happens, we save all the schedule and the orbits down to the station so that it knows everything it needs to know to run. So even if there are sudden weather events like wind or rain or clouds or moon glare, it can make decisions on its own. Can I actually observe this? Should I try to observe something else maybe? And if the network goes down, it still has that information. So it will keep running, it will process the data and do everything locally. And then once the connection comes back, we just upload the data then. And we don't upload the raw images, actually. We only upload the tracking data message that you saw, which is a very, very small file. And that's why we need that huge amount of disk on site and quite a lot of processing power. So, to wrap up, this is an extremely complicated challenge. In order to track all of these hundreds of thousands of objects in space, we're going to need on the order, hundreds of telescopes. And they're all going to have to be coordinated. But I don't think actually the biggest challenge is in designing such a system. That's an engineering problem. We can do that, as I've shown, which is why we wanted to create this telescope to show how it can be done. The real problem is that we need to start collaborating. We need to start connecting the dots, so to speak. And we need to be transparent, because if we have two different actors observing the same satellite, they're going to see different things. It's hard for us to agree completely. And then it's very important to share not only your data, but share how you ascertained it. How did I come to this conclusion of my opinion of where the satellite is? Because what usually happens is that you can find multiple opinions on the position of satellite. And then you need to know how the data was acquired in order to do a merging that actually improves the accuracy and the precision. So what I'm trying to say, we need a shared truth about where things are in orbit. When you're driving your car, and if there's an accident or something and somebody has a dashboard camera, nobody will contest that. Nobody will say, oh, no, that didn't happen. My car wasn't even there. But this happens in space. Because in space, you can say, oh, no, I thought my satellite was 1 kilometer left. Who's going to prove you wrong? So that's why we need a shared truth in order to treat space traffic the same we do traffic here on Earth. And it's not rocket science, but when it is rocket science, as I've mentioned, collaborate with experts, because they will help you create something that actually works. Yep, my name has been Anton Bjöörn, and we help Earth benefit from space. That's our motto at Swedish Space Corporation. Thank you. Okay, I can take questions if you have time. I have time to answer them. Yes? Yeah, I'm sure we're going to see something like that. I know there are satellites that position themselves relative to each other, but I haven't heard of a satellite that actually uses an active radar and then tries to do avoidance itself. What Starlink does, because they have this huge problem because they have so many satellites, is that they have an autonomous system which calculates maneuvers that they need to perform, and then they send those to the satellites. But I can't think of any example where that is done currently, where it's completely automated. But there are efforts to actually remove debris, so you can send up like a satellite and try to grapple it and deorbit it, and then they need radar to be able to do that. But yeah, I think the reason you usually wouldn't do that is because a radar is quite heavy and consumes a lot of power. And the power budget on satellites and the weight, the mass budget is so strict that, yeah, it's very hard to do. Yes?
For how long do you have to observe an object to determine its orbit?
So when we observe an object, we just usually 30 seconds or something for us. We can switch object quite quickly to catch every object passing. But I would say on the order of 30 seconds, you can get maybe 10, 20 frames. Maybe a bit longer if you're expecting bad conditions. Maybe you're expecting half of the images not to be solvable or something. But so it's not that long for a telescope. But what you really need is you need multiple telescopes, because a telescope gives you a really good angular precision. It can tell you at what angle the object was, but it can't tell you how far away it was. So if you have two telescopes quite far separated from each other on the globe, and they observe the satellite as it passes both of them, then you get a really good orbit determination. Yeah. Yes?
In the schedule,
Yeah, so I'm not sure if you are right that we show multiple stations in the scheduler because we have some partner stations that, but they are not fully integrated. They are, so they're more there to show that I mean, when you're designing something, right? You add, if you have one station, you add a few mock-ups just to, so you're constantly designing for a network. But no, we only have one telescope at this point. Yeah. Yes. Yes. Mm-hmm. Mm. Yeah, right now they are launched with the lifetime supply of fuel. I think a satellite might have a lifespan usually of 10 years or so, 10, 15. Yeah, I mean, some have much, much shorter. It depends. If you're talking about a geostationary orbit, so one that is fixed above a point on the surface, they are usually they weigh the amount of like a small car, and they are active for many, many years, probably more than 10. And then if you have a low Earth orbit satellite, maybe like a CubeSat, it might have a lifetime of like 1 year or 2 years. And some of them are not even maneuverable, actually. Some of them have thrusters so that they can do orbit maintenance and sort of change their orbit. And some of them are just launched, put into an orbit, and then they'll stay there for as long as they can, but eventually they'll just burn up or, yeah. Yeah, and actually there's in order to rotate the satellites, you have reaction wheels inside of them. So really massive, or wheels that spin very fast so you can get torque. And I believe there's a limited budget of that as well on some satellites. So after some time, you can't really rotate them. And then eventually you get degradation of solar panels and radiation that breaks down components. So they die. Yeah. But yeah, you can do refueling, but it's currently not done because it's so expensive. Yeah. I hope so. Otherwise, it was recorded, so it will be on YouTube. Yeah. I hope it was interesting.